So we have the basics of space-time diagrams now out on the table. There are a few useful remarks that I want to make about them because they are a somewhat unusual subject. And let me just emphasize or re-emphasize some of the things that characterize space-time diagrams. So let me get one up here, and let me label this guy as, say, x-coordinate and t-coordinate. And let me put up space-time axes for the moving frame of reference in here too. So we know that one of those axes might look like this, and then the other, let me try to get close to something that's reasonable, something like that. So let me label those as well. So that would be the x prime axis, and that would be the t prime axis. Now, first remark is, notice that these axes, the t prime and x prime axis, they're not orthogonal axes, right? We're used to, whenever we change coordinates in basic geometry, we start with axes that are at right angles to each other, and then we say rotate them or we translate them. But in relativity, we see things are a little bit different. So the axes are not orthogonal, but that's okay. There's no mathematical rule that says axes have to be orthogonal. They provide a perfectly good coordinate system, and we've seen how you get the coordinates of any point by drawing lines that are parallel to one or the other axis to figure out the coordinate values of that point. So again, if I have some point over here, all I need to do is draw a dotted line this way, parallel to that axis, dotted line this, parallel to that axis. And these two points of intersection, call them x0 prime, as we've seen, t0 prime, give us the coordinates of this event E in the blue system as x. Let me put it in the correct order there that we're more used to. So let me call this t0 prime and x0 prime. Good. OK, so they're not orthogonal, but they're perfectly good coordinate axes. Second point is, let's just remind ourselves what the meaning of these axes are, right? So here we have all of space at one moment of time from the perspective of the moving frame. This axis over here, this is the origin of the moving frame as it evolves in time. So if someone's standing still at the origin in the moving frame, this is the trajectory that they follow. This is their path through space-time as plotted in the red system. The blue system, of course, the person would say that they are not moving at all. Now, it's also useful just to reemphasize that you can read off key features of the motion of the moving frame by just looking at the slopes of these lines, right? So the slope of this line, the slope of this is equal to the velocity. Again, we're using units where c is equal to 1. So this is the velocity of the moving frame. If you look at that slope, this guy over here, the slope is 1 over v. Again, v is always less than 1. So this is always bigger than 1. So the t prime axis is always sloped upwards in that way. And just by looking at the diagram, you can read off the speed, the velocity of the moving frame. Also note, and it's worth just putting this in for completeness, that if I plot over here, let's say the trajectory of a beam of light, so a beam of light would be at the 45, which would be, say, something like this, if the light beam is heading off into the rightward direction. And as the velocity of the moving frame gets faster and faster, approaches 1, approaches the speed of light, this axis will sweep up toward the yellow line. The time prime axis will sweep down toward it. They'll never cross it because v can't get bigger than 1, so 1 over v can't get smaller than 1, so they'll never cross, but they'll get ever tighter. They'll more tightly hug, if you will, this trajectory of a beam of light. That makes sense. The faster the frame is going, the closer the velocity of a person at the origin will be to the speed of light. Good. Okay, so two other points that I want to make before we move on. point number one is this. When you look at this space-time diagram, it seems not to manifest the symmetry that I have emphasized repeatedly, that the person who is moving can claim to be at rest, and the other frame of reference from that person's perspective would then be moving in the opposite direction. There doesn't seem to be a symmetry manifest in here, and that's clear. It's clear why. We are showing what the space and time axes of the moving frame look like plotted in the coordinate system of the stationary perspective. You don't have to do that. You could take the perspective of the moving frame and plot within that frame of reference what the red system would look like. So just for giggles, why don't we take a look at that? So let me plot down here. Imagine we take the starting perspective to be the blue system. So here is its axis, and let me keep it reasonably close. So that then would be labeled as t prime and x prime. So there is space and time from the perspective of the moving frame. And then from this perspective, which is now going to be considered stationary in the way that we're looking at things, the red system is heading off to the left. And therefore, if you were to look at, say, the trajectory of somebody who is sitting still at the origin of the red system, that person, in this way of looking at things, would have a trajectory, well, that's a little off from the origin, so let me be a little bit better than that. So something like this, good, right? So this will now be the t-axis, and to draw the x-axis, we just, again, take things nice and symmetric about the light trajectory, which would be at the 45-degree angle. Again, as over here, the angle that we have here will always equal the angle that we have over here because of the way the slopes work out relative to the velocity. Same thing in this diagram, but now let me just label it for completeness. So we will have over here, this now will be t, and this will be x. And now you see the nice symmetry. So from the red system, the blue frame is moving, and its space and time axes look as we've drawn. From the perspective of what we initially called the moving frame, now make it the stationary frame, and the other frame is now moving to the left, and we can draw its space and time slices as well. And you see this perfect symmetry between the two pictures. Okay, one final point, which is this. It is really important to always keep in mind what these diagrams mean, right? So we started off by saying that you can illustrate a sequence of events in two ways, as a movie, or you can illustrate a sequence of events by showing the whole history in a space-time diagram. Those are equivalent representations of the same information, and you should always try to keep both pictures in mind. So if we are thinking, say, of this in a movie perspective, the idea would be this is all of space at one moment in time. The next moment in time would be represented, of course, by drawing a parallel slice to this guy. Say, over here, that's a next moment in time, and a next moment in time, and so on. So a movie version of this would show this axis, which is all of space at one moment of time from the perspective of the moving frame, moving in the way that we've indicated here. So this then would be, say, the origin at one moment in time, the origin at the next moment, the origin at the next moment, and so on. So let me show you that just so that you can have that picture in mind when you think about space-time diagrams. So the movie version would look something like this. So here you have a frame moving relative, blue frame is moving relative to the red, and you see that axis, which is all of space at subsequent moments of time, is moving up, and you see the origin is moving along the trajectory we described. These are equivalent pictures. Try to have them in mind when you're thinking about space-time diagrams, and it'll keep you from getting confused and allow you to extract the full information that space-time diagrams are providing us.